on this computer. Okay, so today we're starting, and in fact, for the next 2 or 3 weeks, we're doing chapter 14, which is vector valued functions. So a vector value function you can think of as a curve. So you have a function, let's say r of t. So t is a number, and r of t is a vector in either 2-dimensional space or 3-dimensional space. And we can think of this as a curve. So if you want to think of the variable t as being time, r of t is tracing out the trajectory of some curve in 2 or 3-dimensional space. And in chapter 14, we study the calculus of vector valued functions, or the calculus of curves. And we're going to associate with each curve, each point on the curve, a tangent vector, which is a vector that points in the direction of the curve. And we'll describe all these things. So I find it impossible to draw pictures by hand, but we have a very good textbook with good pictures. So I'm going to switch right now to the textbook and just point to the pictures in the textbook as we talk about all this. So let me share the screen with my book. So you should see chapter 14, vector valued functions, here on the screen. And the basic picture is right here. We're going to look mostly, not mostly, but a lot at curves in 3-dimensional space. So you see the x, y, and z axes, and here is my curve. So as t varies, your vector r of t varies. And r is a point on the curve, and we always write r as having these coordinates, the first, second, and third coordinates, or the x, y, and z coordinates. If the vector changes with time, the coordinates change with time, and we have these 3 parametric functions, x of t, y of t, and z of t, which just tell us the first, second, and third coordinates, or the x, y, and z coordinates of our vector valued function r of t. So that's the picture, right? You just have 3-dimensional space and a point moving in space, right? You look up in the sky, you see an airplane. That's like a vector valued function. It's the airplane moving through space. And here's just another picture of a similar sort of thing. Suppose you have your vector value function r of t, and t goes from a to b. So some number a to some number b, an interval. And as t moves from a to b, you trace out this curve in space. And the way the picture is drawn here is r, the position of the curve at time a, at time t1, time t2, t3 up to b. So you can think of this as a moving particle in 3-dimensional space. And of course, the simplest curve in 3-dimensional space is a straight line, right? So here is a simple problem. You want to find the equation of the vector value function that traces out a straight line from the point 2 - 1, 4 to the 0.306. So the parametric equations of a line are linear. So the x coordinate will be some linear function of x. So x of t will be some x naught plus at. When t is 0, you're at x naught. Y is a linear function of t. Z is a linear function of t. When t is 0, you're at x naught, y naught, z naught. You want that to be the point 2 minus 1, 4. So when t is 0, you want x to be 2. When t is 0, you want y to be minus 1. And when t is 0, you want z to be equal to 4. And when t is equal to when t is equal to, you want t to be moving in the direction of the vector from P to Q. So what is that direction vector? You take the vector from P to Q, its coordinates are going to be 3 minus 2, 0 minus minus 1, 6 minus 4. That's 1, 1, 2. So the direction vector of the line is the vector 1, 1, 2. And so you're starting at the point 2 minus 1, 4. You're going in this direction. So these will be the parametric equations of the line. And this is r of t, your function of the line is a function of t. So this is really what was discussed in the previous chapter, but just take a minute to look at this. And if there's a question, unmute yourself and please ask me your question. All right? This is just a straight line in the plane in 3 space. Now, curves have a certain direction. If you just have, for example, here is a curve in space. And if you just pick a point on the curve and you think of what a tangent vector would look like, or a tangent line at this point on the curve, it's the line tangent to the curve, and it goes in both directions. This curve is unparametrized. We're not tracing it out as in any sense as a function of time. But here, for example, in figure B, we have a circle. And if you look at the direction of the arrows, you see the curve is going around like this. Your point on the curve is moving around the circle in this direction. At this point, the tangent line would go in both directions, but the tangent vector would be the vector at this point, which is tangent to the curve, but pointing in the direction of motion of the curve. So if the curve is going counterclockwise like this, you expect the tangent vector to be pointing in this direction and not pointing in the opposite direction. So we would say this is the positive orientation of the curve because the tangent vector is pointing in the direction of motion of the curve. So at this level, this is really just a very intuitive, not precise geometrical description of what we mean by the orientation of a curve and an oriented tangent vector to a curve at a point, right? If the curve is not given by some function r of t, there's no orientation you can define. But if the curve is given by a vector valued function r of t, there's a natural orientation for the tangent vector at every point. Okay. Now, let me just go back 1 second. So the first example of a curve was a line in space. Right? Our second example is a spiral. So here is a vector valued function. At time t, so t is going to go from 0 to 2 pi, or from minus infinity to infinity. And you get 2 different curves in those cases because If t goes through a finite interval, it's going to be a curve of finite length. But over an infinite interval, the length might be infinite. It might go on forever. So at time t, the vector r of t is given by 4 cosine t plus I sine t, and the z component is t over 2 pi. So we want to understand what is the shape of this curve. What does this curve look like? And one thing we can do is just look at, this is one thing we might do. We'll do it here because it works nicely. Look at the projection of the curve in the xy plane. That is, set the z coordinate equal to 0. Just look at the x and y coordinates. So if you forget the z coordinate, in the xy plane, this is 4 cosine ti plus y equals sine tj. So if you look at this, as t goes from 0 to pi, you should know that this is the equation of an ellipse. This traces out an ellipse. And just to make this clear, let me stop the share for a moment and explain this. So we have r of t in the plane is 4 cosine ti plus sine tj. So this is x of ti plus y of tj. X of t, the x coordinate, is 4 cosine t. Y of t, the y coordinate, is sine t. So another way of writing this is that cosine t is 1/4 x of t. Sine t is y of t. If we square both equations and add, what do we get? We get cosine squared t is 1/16 x of t squared. Sine squared t is y of t squared. If you add, you get cosine squared t plus sine squared t is 1/16. I'll just write x squared plus y squared. That equals 1. So the point x of t, y of t equal 4 cosine t and sine t satisfies the equation that x squared over 16 or x over 4 squared plus y squared equals 1. And that, at this stage, you have to know is the equation of an ellipse, which goes from -4 to 4 on the x-axis and from -1 to 1 on the y-axis. It's this ellipse. So in this curve that we were looking at in the book, if you project it into the xy plane, you're tracing out an ellipse. You're going around and around an ellipse. Let's go back and look at the text. So here is our vector valued function, our curve in 3 space. If you just look at it as projected in the xy plane, it's 4 cosine ti plus sine tj. That's it. And that's exactly the ellipse that I drew a moment ago, right? When t is 0, you're at the point 40. And as t increases, you go around the top of the ellipse to -40, then the bottom of the, around and around and around the ellipse. So if you ignore for a moment the z coordinate, you're going around this ellipse. But you can't ignore the z coordinate forever. What is the z coordinate? It's t over 2 pi. As t increases, t over 2 pi increases, the z coordinate is getting bigger, means you're going up in the positive z direction. So instead of going around and around in the plane, here's this picture in three-dimensional space. As t increases, the projection in the plane is the ellipse, but the z coordinate is going up. So you're spiraling up, just like that. So this vector valued function produces a curve which is an elliptical spiral. Or if you like, you have the ellipse in the plane, there's a cylinder over it, just lift it up and down that ellipse, you get an elliptical cylinder, and our curve is going around and around, up and up and up and up and up in an elliptical orbit on this elliptical cylinder. So this is a very pretty picture that describes exactly what is going on. The cylinder is the cylinder whose base is x squared over 16 plus y squared equals 1, just as we saw a moment ago. Any questions about that? Here's another curve. It's much more complicated. If you just look at it's cosine ti plus sine tj. That's very simple. That's just, if you look at the projection of this curve in the xy plane, cosine ti plus sine tj is just the unit circle of radius 1, whose center is at the origin. So you're going around and around and around in that circle. But what's happening to the z coordinate? It's 0.4 sine 2t. So it's not increasing as a function of t, it's oscillating. This is a sine function. So it goes up and down and up, just the way the sine curve goes up and down. So as you go from 0 to 2 pi, sine 2t makes 2 complete periodic orbits, and it's 0.4 sine 2t. So the z coordinate goes from minus 0.4 to plus 0.4. That's the amplitude of the sine curve, going up and down twice as you go around the circle. And the text describes this as a roller coaster. You're going around this cylinder, which is the unit, whose base is the unit circle centered at the origin. But as t increases, as you go from 0 to 2 pi, you go around this cylinder twice, and you go up and down like a roller coaster. That's what's going on. Now, I don't expect anyone to be able to draw this by hand. I certainly could not. Maple could do it for you, but even that would be a hard programming problem in Maple. But we have this nice book which has very good pictures, and this is a picture of this roller coaster curve. Okay, so we're not studying vectors in this course. We're studying vector calculus, which means we study limits, derivatives, and integrals. And we start with limits. We want to know if you have a vector valued function, what would it mean to say that your function r of t approaches a limit L as t approaches some number a. So r of t is a vector. So as t approaches a, you have a sequence of vectors, and the limit has to be a vector. So here is the definition. It's exactly analogous to the definition of a limit in Calc 1. The vector value function r approaches the limit L, capital L, as t approaches a, if you take the vector r of t minus L, that's a vector. But then you put it in absolute value sign. That means you're looking at the length of this vector. So this is a scalar or a number. And we say that the limit of r of t is the vector L if this limit is 0 as t approaches a. So if R of t were a function of one variable and not a vector valued function, this is exactly what you should be familiar with from Calc 1. Now, in terms of coordinates, there's a very nice way to see what is going on. If the function R has coordinates f, g, and h, then to say that the limit of the vector valued function R of t is the vector L means that the x component of R of t has limit, which is the x component of the vector L. So the vector L has coordinates, x, y, and z coordinates, L1, L2, and L3. And the limit of the x, y, and z components of R correspond exactly to the limits of the x, y, and z coordinates. This is really exactly what you would expect. And we say that a vector valued function is continuous at a point A if it has a limit there, and the limit is exactly the value of the vector valued function at A. So all of the basic properties of limits that you learned for ordinary functions of one variable in Calc 1 carry over to vector valued functions in vector calculus. Okay. So what you need to do is read over section 4.1, do homework problems to get but you need to be able to look at these things, these functions, and sketch in many cases what the curve looks like in space. And the starting point is always to sketch the projection of the curve in the XY plane, because that is very much like an ordinary calculus or pre-calculus problem. Okay. So this is the first section of chapter 14, which is very largely descriptive. And we really start working in section 4.2, which is the calculus of vector valued functions. So I don't want to move too fast or too far ahead, but I do want to at least discuss the derivative of a vector valued function and the tangent vector, on geometrically how to understand or think about a tangent vector. So we take a vector valued function R of t, whose coordinate functions are f, g, and h, f of t, g of t, and h of t. And we suppose that the coordinate functions are differentiable on some open interval from A to B. Open interval means all the numbers strictly between A and B, and we don't consider the endpoints A and B in an open interval. So we define the derivative of a vector valued function exactly, I mean, absolutely exactly the way we define it for an ordinary function. We have this difference quotient. We take a small, we want to know what is the derivative of the vector value function at t. So we take a small number, delta t. We calculate r at t plus delta t minus r of t. This is a difference of two vectors, so it's a vector. And we divide by delta t, this small real number. This just means this is scalar multiplication. This is 1 over delta t times the vector r of t plus delta t minus r of t. And you need to have some sense of the geometry of this, what this means. So let's look at these pictures. Here, figure 14.8, we have r of t. That's the curve that's being traced out in space by this vector valued function. So at some point t, here's r of t. Think of the vector from 0 to this point P on the curve. A small time delta t later, the curve has moved from P to Q. So r at t plus delta t is this vector on the curve Q. And the difference of these two vectors is the vector from P to Q. It's this vector. That's the difference. And we're going to take that vector and divide by this time difference, delta t. So we're going to scale this. So here you have a similar picture. You have r of t, here's r of delta t, and you're taking these vectors. But then you take your delta t smaller and smaller and smaller. So your vectors are approaching r of t, and these difference vectors approach some vector, which is geometrically what we think of as the tangent vector to the curve at the point P. And the curve is oriented because t is an increasing function of time, and the tangent vector is oriented. It's pointing in the direction of the curve. So here we have a curve, and here at the point P is the tangent vector. It's like if something were moving on a string, and right here, you cut the string, it's going to fly off in a straight line, and that's the straight line direction it's going to fly off on. Are there any questions about that? So here is a kind of a long calculation to convert things from vector equations to coordinates, to scalars. So r prime of t, the tangent vector or the derivative, is defined as the difference of these vectors divided by delta of t. But if we write these vectors in terms of the coordinates f, g, and h, we get this vector minus this vector. If we collect the I, j, and k coordinates, or the x, y, and z coordinates, we get this. And if we separate these out, it's this times I, this times j, this times k. But each of these is just the ordinary derivative from calculus 1. So we have this formula for the derivative of a vector valued function in terms of its coordinate functions. It's exactly this. So this is summarized in the definition that if you let r of t be the vector whose coordinate functions are f, g, and h, then if each of f, g, and h is differentiable, then this vector valued function is the derivative of r of t. And if this is different from 0, if it's not the 0 vector, then we call this a tangent vector at the point r of t. So a tangent vector at a point is just the derivative of the function at that point. So of course the derivative has to be defined, and we only say it's a tangent vector if it's not the 0 vector. So here's a very simple example. Here's the function r of t. Coordinates t cubed 3t squared t cubed over 6. The derivative, you just differentiate each coordinate function separately. You get 3t squared, 6t, t squared over 2. If you take this vector valued function, the derivative is exactly what you get by differentiating the x, y, and z components separately, and you get this. Now, very often, what you really care about is the direction the tangent vector is pointing in, not what its length is. And so you often take your tangent vector and divide by its length, and now you get a vector of length 1 pointing in the same direction as the tangent vector, and that is what is called the unit tangent vector. So the unit tangent vector of a curve at t is the derivative of the function at t divided by its length. This only makes sense where the tangent vector is not 0, because you can't divide by 0. So here's a simple example of that. If you take r of t to be t squared 4t and 4 log t, the derivative has coordinates 2t, 4, and 4 over log t. 2t, 4, 4 over log t. And what is the length of this? Well, the length of a vector is the square root of the sum of the squares of the coordinates. Do the calculation. This is what you get. So this is the length of the unit tangent vector. So if I take this vector and divide by this, I get the unit tangent vector. The tangent vector divided by its length is the unit tangent vector. So in Calc 1, you learn lots of formulas about derivatives, like the derivative of the sum of two functions is the sum of the derivative. You learn the product rule, the quotient rule, the chain rule. Each of these has analogs for vector value functions, and they're collected in theorem 14.1. So for an ordinary function, the derivative of a constant is 0. Same is true here. If you take a vector valued function, which is the constant vector c, the derivative of the constant function is 0. The derivative of the sum of two functions is the sum of the derivative. If you take a scalar function times a vector function, you get the product rule. Right? If you take a composite function, a vector function composed with a scalar function, you get the chain rule. And there's also a product rule for the dot product, almost exactly what you would guess, and for the cross product. And it's not hard, but I'm not going to do it, to check all of these by taking your vector valued functions u and v and your scalar function f, writing everything in coordinates and doing this calculation. And we define integrals in a completely analogous way. So if you have a vector function r of t, an integral or an antiderivative is a vector capital R, such that each coordinate is the antiderivative of the coordinates of the original function lowercase r. So you just take little f of t and integrate to get capital F and so forth, and you get the integral or the antiderivative of r. And so this is just that written down clearly. If r of t is this vector valued function, and if capital F, G, and H are antiderivatives of the lowercase f, G, and H, then the indefinite integral of r is this vector plus an arbitrary constant c, where c now means constant vector and not constant number. So for example, here's an exercise. You only can do this if you know calculus 1 and 2, but that's a prerequisite. So here I have a function, a vector value function. I want its integral. So I have to integrate all three of these. I have to integrate this, this, and this. So the integral of this, well, square root of t squared plus 2. The integral of this is minus a third e to the minus 3t. The integral of the sine is minus the cosine. So you do the integrations and you have solved the problem. And of course, a definite integral is defined in exactly the same way. So you have the definite integral of this, you find the definite integral of the x, y, and z coordinates respectively. Okay. So that is all there is to the first two sections of this chapter. Let me stop the share and just do a couple of problems so you can see what one does in practice. So I'm just doing some exercises from the end of this section. Number 17, we have the function r of t equal to t, 3t squared, and t cubed. And the problem is to compute r prime at 1. So in general, at any t, what is the derivative? You differentiate each coordinate separately. The derivative of t is 1. The derivative of 3t squared is 6t. The derivative of t cubed is 3t squared. So that's the derivative of r. And when you evaluate this at 1, you get 1, 6, 3. So that's the answer. Let's look at number 24. Suppose we have the vector value function r of t equal to cosine of t, sine of t, and 2. T goes from 0 to 2 pi. What is r prime of t? It's minus sine of t, cosine of t, 0. What is the length of this vector? It's the square root of minus sine t squared plus cosine t squared plus 0 squared. That's the square root of sine squared t plus cosine squared t. That's 1. So this vector has length 1. So the unit tangent vector is just this vector divided by its length, which is just this divided by 1. So it doesn't change. It's minus sine t cosine t 0. That's the unit tangent vector. Suppose we had the vector valued function r of t equal to t, 2 over t. What is the derivative? R prime of t is 1, 0. The derivative of 2 over t is minus 2 over t squared. The length of this vector is the square root of 1 squared plus 0 squared plus minus 2 over t squared squared. That's the square root of 1 plus 4 over t to the 4th, or the square root of t to the 4th plus 4 over t to the 4th, which is 1 over t squared, square root of t to the 4 plus 4. So the unit tangent vector is r prime of t divided by the length of r prime of t. If I divide by this, that's t squared over the square root of t squared plus 4 times the vector 1, 0 minus 2 over t squared. So that's the vector t squared over the square root of t squared plus 4, 0 minus 2 over the square root of t squared plus 4. So this vector, if you check, it does in fact have length 1, I hope. Let's see, something is incorrect. Let me just double check everything. R of t is t2, 2 over t. The derivative is 1, 0 minus 2 over t squared. The length of that is the square root of 1 squared plus 4 over t to the 4th, which is t to the 4th plus 4 over, oh, sorry. Right, so this is t to the 4th. I just wrote this down wrong. T to the 4th. And now this is fine. T squared over the square root of t to the 4th plus 4, comma 0, minus 2 over the square root of t to the 4th plus 4. So this is the unit tangent vector. Any questions about that? Let's look at a couple of integrals. This is number 59. R of t is t to the 4th minus 3t, comma, 2t minus 1, 10. So this is my vector valued function. The integral of t to the 4th minus 3t from calculus is 1/5 t to the 5th minus 3/2 t squared. The integral of 2t minus 1 dt is t squared minus t, and the integral of 10 is 10. So the integral of r of t dt is, you integrate each coordinate, you get 1/5 t to the 5th minus 3/2 t squared, comma, t squared minus t, comma, 10t, plus any vector. That's the integral of the vector valued function. Okay. Let's do a few more examples. Let me pick some that use the chain rule. So, chain rule said the following, using the notation of our text. If we have a vector value function u, scalar function f of t, we have this composite function u composed with f of t. So you have a number t, f of t is a number, and then you evaluate your vector value function at f of t. And what is the derivative of this? By the chain rule, this is u prime evaluated at f of t times f prime of t. Okay? That's the chain rule. So for example, if we this is number 44. U of t is 1t squared. So let me do this in two different ways. What is u at t cubed? That's 1 t cubed squared, t to the sixth. So u prime, the derivative of u of t cubed will be 0, 3t squared, 6t to the fifth. You just differentiate each of these coordinates. But then we use the chain rule. So this is, if you have f of t equal to t cubed, I want to find the derivative of u of f of t. It's going to be the derivative of u evaluated at f of t times f prime of t. What is that? Here's u of t. So u prime of t, you differentiate each coordinate 0, 1, 2t. F of t is t cubed, so f prime of t is 3t squared. So if I compute u prime at f of t, f prime of t, u prime of t is going to be 0, f of t, 0, 1, write this more legibly. This is going to be 0, 1, where's my u prime of t? Yeah, 0, 1, 2f of t times f prime of t times 3t squared. So that's the scalar 3t squared times 0, 1, and 2f of t, 2t cubed. That's equal to 0, 3t squared, 6t to the fifth. It's exactly what I got previously. Okay. We have a product rule for the dot product that said the derivative of the dot product of two vector value functions is the derivative of u dot product with v plus u dot product with the derivative of v. So for example, let's look at number 37. If u of t is 2t cubed I plus t squared minus 1j minus 8k, and v of t is the vector valued function e to the ti plus 2e to the minus tj minus e to the 2t k. If this is u, what is u prime? The derivative of u is 6t squared I plus 2tj plus 0. The derivative of v is e to the ti minus 2e to the minus 2tj minus 2e to the 2tk. So this is the formula for the derivative of the dot product. It's u prime dot v. So u prime dot v, that's, let me write this out. This is 6t squared I plus 2j dot product with v plus u two t cubed I plus t squared minus 1j minus 8k dot product with v prime. And when you calculate this, it's kind of a mess, but you get the dot product of these. I have 6t squared e to the t plus 2 times 2, 4e to the minus t, and 0 times something, plus this dot product, 2t squared e to the t minus 2 t squared minus 1 e to the minus t minus 16 e to the 2t. So if I add that up, 6 plus 2 is 8 t squared e to the t. I have 4 e to the minus t plus 2 e to the minus t plus 6 e to the minus t minus 2t squared e to the minus t minus 16 e to the 2t. That's what it is. Okay. So that is the elementary vector calculus for a vector valued function. All right. Oh, so we actually did a lot today. Of course, it's quick and easy to go over, but it takes some time for you to read through carefully the text and do exercises. As many as you can do, the more you can do, the better, certainly. And then tomorrow, I'm going to talk about the simplest physical interpretation of these things, where your vector valued function gives you the position of a particle in space. The derivative is a vector valued function, which is the velocity of the object. Speed is defined to be the length or the magnitude of the velocity vector. So velocity is a vector, but speed is a scalar. And if you take the velocity vector and differentiate it, which is now the second derivative of the position vector, you have what is called the acceleration in physics. And so we'll talk a little bit about position, velocity, and acceleration in space. This is a lot of the problems we do will be very similar to what you did in Calc 1 and 2, but a little bit more sophisticated now. And now we can also consider three-dimensional motion as well as two-dimensional. So tomorrow we'll study position, velocity, and acceleration. And next Monday, we talk about the length of a curve. And then the following recurvature and normal vectors, and then we're done with the chapter. Any questions? If not, then the ambient noise is getting pretty bad, and that's it for today. So be well, everyone. Next class is tomorrow, Thursday. You follow a Monday schedule for all your classes.
All right, thank you, Professor. Have a great day.
Thank you.
Sorry, speak up, please.
Have a great day, Professor. Thank you.
Thank you, you too. Bye, everyone.
Bye.